Right. So the last day we dealt with static electricity. Um, but today we're going to talk about current electricity. Right? And you'll see why we call it current or it's flowing. Yeah. So in contrast to static electricity, which there needs to be some kind of build up of charges, and then it causes the charges causes ionization and then moves across or discharges itself. With current electricity, there's a flow of charges, electrons in particular. Uh, and then we can talk about, under this topic, we're going to talk about direct current, and then we will talk about alternating current, right? You hear of DC and AC, right? Sometimes they don't use the dot. Let me speak of current electricity. The electricity we'd be talking about will involve either direct current or alternating current, right? So what's using a word here? What do we mean by this word here, current? Right? Well, basically, current is a flow, right? It's a flow of charges. It's a movement of charges, right? As a matter of fact, that's how they define current electricity, right? Remember, we said in static electricity, we have charges that are stationary, right? But in current electricity, well, that involves a flow of electricity, which we will call a current, right? The flow of electrons is what we'll call a current, and current is depicted by the letter I, capital I, right? And it's measured in something called amperes, amperes, right? Ampere. Um, the symbol is E, right? Capital E. And if you were to, do a little more physics, and so you'll see that, as we said, um, charges. Um, well, we talked about electrons and protons and so last week. Electrons carry a certain charge, and then you hear of current is the rate of flow of charges, right? Where Q refer to the charge, and this is time, right? But we're not going to get into so much of that. We're just doing the basics. Good. And as we said, current can either be of two types. It can be direct current. And why they call this direct current is that the current is going to be flowing in one direction all the time, right? The flow of current is in the same direction all the time. Whereas alternating current is where, well, okay, we'll talk about why we're saying in direct current is flowing in one direction in just a moment. While alternating current involves an oscillating, an oscillation or a changing periodically of the direction of the current, right? And we'll talk about them in detail in just a moment. Good. So as we said, the unit for current is the amperes, right? And all of these are names of people that they borrowed from. These units. Maybe this person did a lot of work in the area of electricity, and they borrowed his name to name the unit of current. The symbol is capital A, right? And no doubt you too yourself, you can hear of multiples and submultiples of amperes, right? Like you can hear milliampere, right? So you write M milliampere, right? And the current can be very large, and you can have kiloampere as well, right? So like in the current that is flowing around in your electronics, like your phone, is very small, right? It might be of the range, the milliampere range, or even microampere range, right? But I'll safely say it's more of a milliampere range, very small, 0.001 of an ampere, right? Very, very small currents. And for that reason, a lot of people, they don't fear direct current, right? You don't have much to fear because usually you will be dealing with small voltages as well as, but I shouldn't use that word voltage so early in our discussion. I'm coming to that, what that is. But the current is also small, and it doesn't do any harm to our body, right? And I'll tell you when though, I'll tell you when you can have situations where direct current is large enough to harm the human body, right? I'm coming to that. Let me just introduce, the basics, right? I'll get into the other things later on. Yeah. So how do current flow? And here we're talking about direct current, right? So we're moving to direct current. So in direct current, let's say you have a circuit, you have a circuit, and let's say you have a bulb, right? You have a bulb and you connect, okay, this part and this part here, right? So let's say down here is negative, down here is positive. This is maybe a power source, right? So this is a bulb and it's glowing, light it up, right? So when you have this setup here, electrons flow from the negative side to the positive side of your power source. And as it passes through the bulb, right, or the light source, and again, I'm going to use some words that need some more explanation, but you will get the explanation. So the bulb would, create some resistance, and whatever is going to happen, some kind of reaction is going to happen there, and going to produce light and all of that. Yeah. But really and truly, when you have direct current flowing, the electrons flow from the negative side through what you call the load, right, to the positive side. However, before electrons were discovered, right, and they understood that, well, when a current is flowing, it's electrons really that is flowing, and it's flowing from the negative side of the power source, like a battery, to the positive side. Before they discovered all of that, they had already sat down, and there'd be at these conventions. So again, we take another bulb here, right? So it's glowing, and as we said, this is negative, this is positive, and they had already, come together and decided, look, we don't quite understand the flow of current yet, but we are going to see that current flows from positive to negative, right? So that's what you'll hear them say conventional current flows from positive to negative, right? So when sometimes you see they draw circuit diagrams and you see the current flowing from the positive side to the negative side. When in reality, it's electrons that are flowing from the negative side to the positive side. But as I said, before they discovered electrons and so, right? And protons and neutrons and all of that, they didn't know about those things, right? They observed how electricity is behaving. I said, man, we got to say how this thing is flowing, right? And they all said, all right, we can say that electricity, direct current in particular, is flowing from positive to negative. As a matter of fact, direct current was discovered way before alternating current, right? Now, what causes the flow? What causes the flow? And that brings us to the force, right? The force that is causing an electron or electrons to flow. So if you have like a battery, you know, and I'll use a symbol maybe. This is how this is how you draw a battery, right? So let's say it goes through a resistor there, right? And I'm putting a little symbol. I should draw that better because I don't want you to confuse it with all right, let me not put in a resistor. Let me not put in a resistor. Let me probably put a bulb back, right? So we have a little bulb here again, right? So we got a bulb and right, and it goes like this and it comes like this. Good. Now the power source, right, or the energy source is going to produce something called an EMF, right? Some use common, some use capital. An EMF, which is an electromotive force, right? So the power source or the energy source, whichever you want to say, creates something called an electromotive force, right? And that has to do with the elements that are inside the battery or the generator that you have or so. It creates a certain difference here where, okay, this is positive and this is negative. And this now, this electromotive force, right, creates a current through the circuit. And as it creates a circuit, a current through it, what happens, what causes this current to it is that it causes a potential difference, now you call this PD, PD, right? Or something is common P, common D, right? Potential difference. This electromotive force creates a potential difference across this. Well, in this case, let's say it's a light bulb, you know, it's a light bulb. So over here is positive, down here is negative, right? And what happens? Well, all right, I think we going against our own convention, right? I know the notes said we're going to consider electrons flowing from the negative to the positive, but current, we're going to go with current flows from the positive to the negative. So this potential difference that is created here, right, causes, well, the current to flow through this little element to the circuit, and well, it does what it does, you know, if it's there to give light or what, right? But this potential difference really is created by this electromotive force, right? So the electromotive force really comes from the power source or the energy source, right? And that sets up a potential difference here, right? So when the circuit is closed, right, it kind of pushes electrons around the circuit. It pushes it. The bulb that you have here is going to resist it and so, right? But because if this is great enough, it's going to cause the current to flow, right? And again, I'm going like, I'm using how the electrons will flow. But remember, we're going with current flowing from the positive side of a power source to the negative side. And as I said, this electromotive force induces a potential difference here, right? And I'll put a letter here for you to V, right? V. And that's what we call voltage, right? So electromotive force is measured in volts, right? As well as potential difference is measured in volt, right? And if you were to, take something called a voltmeter and put it across here, notice when we talk about parallel and so, right? And if you were to put what you call an ammeter here, that will measure the current flowing through here, right? So we're getting introduced to different um, quantities, right? In electricity. We talked about current, we talked about electromotive force, we talked about potential difference, right? And their units, right? Current is measured in amperes, electromotive force and potential difference is measured um, in volts, right? And you hear this word a lot, voltage. They'll say the voltage of the battery is 12 volt. You know, you understand? They'll tell you that they might tell you that this bulb is rated at uh, 6 volts and 12 volts and so, right? So yes, you hear those terms, right? A shortened form of electromotive force you'll see we'll use later as just E, a capital E, right? And for potential difference, you might use a capital V, and that's it, right? And again, depending on what you're dealing with, you can have instead of volts, you can have kilovolts, right? You can also have millivolts, millivolts, right? If you have very small um, potential differences in the circuit, and even if your battery is a very small one, like in your cell phone and so, right? Some of those circuits in there would work with millivolts. I mean, your battery in your phone might very well be maybe a 6 volt battery or so, right? 6 or 7 volts, somewhere there, right? 6 point something going on to 7, right? So your battery in the phone is very small. All of you are familiar with your car battery that has 12 volts, right? And I did mention to you that we hardly worry about the safety of direct current, right? Um, we hardly worry about it. However, I'll tell you this. Electric cars is becoming popular, right? I saw the other day they were having some kind of car show or some kind of show in Georgetown, and there's this company, a Chinese company. They have like an agent here in Guyana, BYD, and I think some of those cars will have as much as some of them will have like 196 volts, right? Well, this here, a voltage of this magnitude can very well give you a terrible electric shock, right? It can even be fatal, right? It can be even be fatal, right? So you don't play with those. If you ever to look into an electric car's it's electrical setup, you'll see it's a large orange insulation. And the reason why those insulation and those wires appear very, very large because you're dealing with large current. You're gonna drive a motor that would move a car, right? And electric cars are very powerful. Some of them would beat out what you call it, a gasoline car, right? Or a diesel engine. They are very, very powerful. So this, I'm giving you fair warning that while generally you take your hand and you hold the 2 lugs of a battery and you laugh, right? You take a cell that you put in like your remote, and you don't risk an electric shock from those. But with an electric car, well, you're talking about something else, right? I know long ago, y'all ever see those 9 volt battery that certain things still use them, a 9 volt battery. Um, I don't know if any one of you know them. They're kind of square. There's a square battery like, right? And they have like one part there and then another here. I don't know if anybody knows of them. And when you put your tongue on this battery, it actually gives you a small shock. because it's 9 volts, right? And some people, when they put their tongue on it, as a kid, I did it, right? I did it because I heard from friends that it does give you a little electric shock. And I actually put my tongue on it and give you a little ning ning, a small something, right? If you put it on a child's mouth, don't do that, right? Why did I even say that? It will give them a little zing. I think even a big person, you might get a little zing from it, right? I don't advise you to do it, but I'm just telling you as a kid, and we were more adventurous and so, right? And we did it as a kid, and yes, right? So
Sir, excuse
yeah,
me.
yeah,
One time I had to do an electrolysis lab for chemistry,
uh-huh,
and one of my classmates, he had the voltage on the voltmeter to 10 volts, and he took the alligator clips and placed it on his tongue and got shocked.
yes, yes. It would give them a zing, right? Yes, it will give you a little zing on your like the places like your tongue because your tongue is very moist, and the thing will just go across that. Remember, electricity has a way of taking the path of least resistance. So because the tongue is moist, it's going to jump right there. But if you were to hold it with your two hands, one in your right hand, one in your left hand, 12 volt will do you nothing. You laugh at it, right? You take a 12-volt battery in your car, you put your hand on positive and negative, and nothing happens. But if the two poles were close enough, you put it in your tongue, you'll get a little zing. Good. Another component of direct current circuits and alternating current circuits as well is what we call resistors, right? Resistors. And resistors are placed in circuits for a number of reasons, right? Well, as a matter of fact, most components in electric circuits would have some kind of resistance, right? Let me use the word resistance, right? If not all, every component inside of a electric circuit, whether it's a direct current circuit or a alternating circuit, current circuit, there's the components are going to have some kind of resistance, right? And resistance is measured in something called ohms, right? I write out the word ohms, and this is the symbol here, right? That's the symbol. It's kind of sharp, right? It's a Greek letter, right? It's a Greek letter. And then you can have resistors that go from um, maybe 1 ohm, 10 ohm, 100 ohm, and you can have kilo ohm as well. Kilo ohm, right? You can have kilo ohm, right? And so, right? So you can have that, right? You can have ohms, you can have kilo ohms, you can have mega ohms and all, right? Depending on how much resistance is there. As a matter of fact, you can actually, I remember, no, I think my multi-tester, I have a multi-tester. It cannot test the resistance of my body. Like if I hold the probes in my right and left hand, it will register an open circuit. And again, the reason why the battery inside there is so small, it can't send a large enough current to my body, right? And that's what I'm saying again. We don't really, we're not very afraid of direct current unless the voltage is large, like in the electric car, right? And you'll see the symbol we use here is R, right? Right? R is the symbol, and the unit for resistance is the ohm, right? Is the ohm. Good.
Oh,
Huh? Somebody said something. So now that we talk about current, we talk about current, we talk about voltage, we talk about resistance, right? Well, there was a famous scientist who tied the three together, right? And his name was Ohm too, right? Ohm's law. He came up with this law, right? Where he connected these three things, and you can write it differently. That the current flowing through a direct circuit, right, is equals to the electromotive force divided by R. Right? So he came up with this relationship. And this here is verified by experiments, that the current flowing through a circuit is going to be equal to the electromotive force divided by the resistance. Right? And of course, you can rearrange this differently, right? I've seen it in this form, E equal IR, right? And a modification of this is that when you're dealing with a circuit, let's say, all right, you have this is a battery. Let's say you have a battery, and oh, I forgot to show you when you have in a circuit a resistor. This is how you would indicate a resistor in a circuit, right? So let's say this is some resistor, and the resistor has a voltmeter connected across it, right? To measure how much volts is across this resistor, right? And let's say the current flowing here is I, right? I, capital I, right? Well, instead of writing it with E, if you're dealing with just this resistor, you say V is equals to IR, right?
So one question. You get the triangle, the VI and R.
Yeah, I think in the notes I got that. Yeah. If you're into a memory aid, yes, that triangle can
that
work.
is
Yeah.
easier.
Very nice. At least you're going through the notes. That's nice. Yeah. Right?
I'm an electrician, sir.
Oh, great. You're supposed to be teaching this class, boy. Right? Am I right so far that we don't have to fear direct current unless we're dealing with something like an electric car?
Yeah, that's right, unless it's a high voltage.
Yes. And most everyday applications, like your car battery. Oh, I'll tell you what, we're not going to deal with that in this course, but I bought a capacitor bank, right? And I was warned that when it's charged, like inside your what do you call it? Your microwave, there's a capacitor in there. Don't fool around with that one, right? Any capacitor bank, the reason why is that those things discharge they charge very quickly, right? So it gives you a large current spike that would very well hurt you, right? Give you a good ning. Yes, I have a capacitor bank that I bought for a battery. I was told, like the car battery, like, okay, let me just tell you this here. This is just by the way. This is not our class. You see, when I see there's a electrician in the class, right away I got sidetracked. So if you have a car battery, right? You have a car battery. And every time you crank up your car, it's kind of working this battery. Oh my, you did something to my yes. Oh, you're not doing it. All right, good. Yeah. Yes. Y'all hearing me, right? Yeah. So every time you do this, you do a start, right? On your car, it really drains out this battery. And it works the chemical process in this battery. So what instead we can do is connect a capacitor bank, right? So you get a capacitor bank here, a 12-volt capacitor bank, right? I think they're not 12. I think they're 60. I think mine is 16 volt. And what it does, this battery will slowly charge this capacitor. So when you start your car, it's going to drain the capacitor and don't work the battery because the capacitor has a very small resistance. So it will drain the capacitor out. And then as you go along, the battery will slowly charge back the capacitor. So in that way, you could actually don't have like a big battery in your car. You could have a small 12-volt battery and you don't have to worry, it will start it. Right? I bought it, I have it somewhere on the shelf here. I didn't buy it from a car. I bought it for I have a battery system in front, and sometimes when I put on heavy loads in it, it will kind of make the inverter make a song, you know. Anyway, that electrician fella is the man who got me distracted and got me started with all these things. Yeah, yeah, we were talking about Ohm's law, right? Ohm's law, and I'll just give you a quick example. It's in the notes. Let me cut it quickly and bring it across. This is an example. One second, let me just put on this fun thing. So look at this example here. So here it is. We have a 10-volt supply, right? So the energy source is a 12-volt battery. And there's a 5-ohm resistor in the circuit, right? Well, keep in mind that the notes that I'm cutting this from, they treated the flow of current from the negative to the positive. As I said, conventionally, we say that current flows from the positive to the negative. So don't kill me for that. I just borrowed it from the notes, right? Yeah. So we're not worried about current, the direction of flow here, right? We're worried about, well, how do you relate these three quantities? The three quantities are related by I equal E over R, right? So in this case, all right, let's say you want to know what's the current flowing in the circuit. Well, if the battery has an EM or electromotive force of 10 volts, and there is a resistance of 5 ohms, and in this case, we are thinking the wires of this circuit as though it has negligible, resistance. We're treating it as though it's zero, right? So we calculate the current using I equal E over R, which is 2 amperes, right? And that's how you use the formula. Good. So let's talk a little more. We want to get in now to DC circuits a little more, right? I think most of us, we will not be working with DC circuits in real life unless maybe what? There are people who would do what kind of work they'll do probably. Some electronics technicians will deal with DC current somewhat. But most of the time you'll be dealing, because in electronics, you find DC circuits mostly in electronics, right? And because what happens is that most electronic equipment you have in your house will take the AC power that you get from GPL and convert it to DC. And then they'll split up that voltage and send it here and there to do all the little functions, right, that electronics is designed to do. So unless you are an electronics technician, you will not be exposed too much to DC circuits. You will mostly be exposed to AC circuits, which we're coming to in just a moment, right? I want to say though that not because your electronics, I mean the whole setup in there might be using DC current. Don't think that you can handle it anyhow, because remember, in your electronic devices like let's say your TV. Your TV would take 110 power or 220, depending on the type of TV, and convert it to DC. So that part, there's a part in that TV that you don't want to be playing around where the 110 and 220 is located, right? So now because I'm saying that, electronics largely run on DC power, meaning that you can go in a TV or you can, go into a music set, an amplifier and fool around like your head and go, no, because there is a little part there, right? That where the AC comes in and you're still dealing with 110 volts or 220 volts. And I'll tell you the story quickly. I remember one time my friend, he had a computer that was shocking him and his family. So he called me because in those years I used to be a electronics technician, electronics technician. I used to do electrical work as well, right? So he called me, he said, man, his computer is shocking everybody that touches it. So how are your computer shocking you, man? Anyway, when I checked out what happened, for some reason, um, the part where the AC power card went into the power supply, it was pinched by the metal frame. There was a pinch, right? And that made the entire, those times the computer box, the entire CPU, the frame used to be made of metal. It still is, right? Some of them, I think mine here, let me see. No, mine is plastic. But those years it used to be metal. So, and aluminum at that too. So when they touch their computer case, it used to shock them. So I said, man, but even so, and the electrician guy in the class here should tell you, if there was a ground wire attached to the point that they were using, that should have taken the current to the ground. Am I right, friend?
Yes, sir.
And guess what I found out? They did not have a ground wire in their entire house. I don't know who wired that house. There was no ground wire. I said, what? You're playing with the life of your family here by not having a ground wire in the house. Anyway, we had to remedy that, right? Because the electrician simply didn't wire the ground wire, you know? While the ground wire was present in the white wire that was in the entire house, yes. He didn't connect it in the, well, those years we used to go what you call fuse box, right? It wasn't those these circuit breakers we had. Those were long years. Eh? The guy never wired that ground wire to the ground. So anyway, I fixed it up, and I also take out the part of the wire that was pinched between the frame. And well, they weren't. Of course, I taped it up and insulated it well, and so, and it was okay. Yeah. So even though I am saying right that your electronics largely uses DC current and very small voltages and currents at that, don't forget that most of your electronics, right, might very well be running off a 110 volt or a 220 volt outlet. And when you have that situation, there is a part of the electronics in there that might very well have 110 or 220, right? And you still need to be careful because AC messes with your nervous system and your heart and so on. You can get an electric shock, right? We're coming to that a little later. Good. Let's talk a little more about electric circuits, right? And we're going to talk about where, and we're talking about DC circuits where you have resistors in series, right? In series, right? So this is where, okay, you have a power source, you know, and what you could have is several resistors. Why am I working hard when I have a diagram in my notes? What's going on with me, man? What's going on with me? 1 second. Yeah. So look here. So here you have a DC circuit where they have several resistors, right? This is an 11 kilo ohm, 2 kilo ohm, and so on, right? There. And now, if you want to do any calculation with this circuit and you want to find maybe, okay, let's say we want the current that is flowing. And we're coming to an example just now, right? Now, to get the total resistance, remember we might want to find the current flowing through the circuit. And in such a circuit, when the resistors are all in series, the current through them is going to all be the same because there's only one path for this current, right? And again, I know in this diagram, they're showing you as though it's going from negative to positive, right? All right, let's not fight about that. But because there's only one path for this current, the current in this circuit is of one value. The current, you notice I subscript T is the same as I subscript 1, meaning the current through R1, I subscript 2, which is the current through R2, and so on. They're all the same, right? They're all the same. And to calculate that current, first you need the total resistance of this circuit. And when resistors are in series, you simply add them up, right? As you see here, add them up. The total resistance of this circuit is 16,100 ohms. Right? So when resistors are in series, the total resistance is formed by just adding them up arithmetically, right? You just add it like you would add a set of numbers. We got it? Good. Let's say you want to calculate the current. Let's maybe use one. Yeah, let's use one. There's another one inside the notes again. Let me go to that one. Another example. Let me not kill myself to draw, you know. And you'll see how useful that Ohm's law formula is. This formula that has to do with. So look at this. Look at this circuit here. You have a 12-volt battery and it drives a current through these resistors, right? So if you want to know the current in this circuit, right, first you have to get the total resistance, add all of them up together, and you use I is equals to V over R, right? In this case, it's not V. This is the E over R, right? The electromotive force, which is 12 volts. That's what the battery is producing. 12 volts over total resistance is 1K ohms, which is 1,000 ohms. And as you can see here, the current is very small, 12 milliampere, very, very small, right? Good. So notice these meters here, right? These meters. So if we were to measure the voltage across all the resistors, it will be the 12 volt that you see, right? It's the same as the battery. However, the voltage across this R3 here, as a matter of fact, if you want to calculate the voltage across any resistor, it will be what we said, V equals to IR, right? So once you found I, and that's what we found here, right? We found here. So the voltage across this one here is going to be what? V equal 0.012 ampere multiplied by 250 ohms, which is, and it should give you that 3 volts that they have there. Right? So if you want to know the voltage drop or the potential difference across this resistor, in other words, what will a meter read if you were to put it across here? Well, it's going to be 3 volts. And you can calculate this as well. You can calculate that. I'm talking about, okay, if you were to put the voltmeter across there or across there, use the same formula, V equal IR. Right? Is that easy enough? Good. Let's go to parallel DC circuits now. Parallel DC circuit. No. Yeah. Parallel DC circuits. Right? So in a parallel DC circuit, things are a little different, right? The resistors now are arranged in a way that the current can flow in different paths. You see, current can flow through here, current can flow through here, right? And they all join up back and go back there. In this case, if I'm to put a voltmeter here, if I'm to put a voltmeter here, it will be the same as the reading on the battery, right? So if down here is 12 volts, this voltmeter is going to read 12 volts. In other words, the voltage across each resistor is going to be the same 12 volts. And you will see how having parallel circuits is very useful when we go over to AC current, right? And the electrician in the class will tell you how parallel circuits is predominantly used in your house and so with AC circuits. We're coming to that, right? So in a parallel circuit, when the resistors are arranged like this, the voltage from the battery is shown up at the terminals of these resistors. However, the current through them, that's different. The current is going to be different, right? So because the current through here, I1, remember, is going to be equal to, they have it here, E divided by R1, and I2 is going to be equal to E divided by R2. And this total current here, IT, is going to be the sum of I1 and I2, right? Notice in parallel circuits, it offers alternative pathways for the current to flow. And that is why you have a different current here, a different current here, right? But down here and here is going to be the sum of these two, because it's like, you can see it, right? This current flows here, this one current flows here. And because they're in something called in phase, I don't want to get into all of that. The flow of this current is in phase. They add up. You can add them up like this, right? And this is the kind of circuit you will see a whole lot in AC circuits. It's what you use in your entire house, right? Your entire house. How do you add up though? How do you add up though? Resistors in parallel. Let me, I'm losing my voice already. Good. So when resistors are in parallel, the effective resistance or the overall effect of all these resistors is not like DC circuit series circuit where you just add them up. No. Right? The relationship that you have to use is this one here. Look here. 1 over R total is equals to 1 over R1 plus 1 over R2 plus 1 over R3. Well, remember, we don't know how many resistors are in parallel, right? Of course, if I ever give you something like this, I might not exceed 3. I might not even exceed 2. So R1, remember, you have to flick, when you add all of these up, you have to flick them over, right? So R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3, right up to 1 over Rn, right? So the mathematics gets more difficult, right? It gets more difficult. And I do think they have an example. Yes, they do have an example. Let me bring that example. 1 second. Take some cutting here. No. All right, I think, all right, so this is it here. I'll write out the solution. They have it on the other page. Yeah, so you have this circuit and you want to know, well, what's the total effective resistance that this circuit is going to produce, right? Because maybe you need it to calculate I, right? The current through here, right? I total, you might want to know that. Good. So let's take these three. So it's basically what? 1 over 5 ohm plus 1 over 10. Leave out the unit, right? 1 over 20, right? See that? They use some arithmetic there, right? So 1 over 5 is the same as 4 over 20. 1 over 10 is the same as 2 over 20. They're finding the LCM of 5, 10, and 20, right? And then 7, what is it? Sorry. 1 over 20, 2 over 20. Oh, and then 1 over 22, right? 1 over 20. When you add up all this, you get 7 over 20. And to get R total now, you have to flick this over, right? Which is equal to 20 over 7, which is approximately 2.86 ohms. Right? 2.6 ohms. So that's a little bit of mathematics there. It's a little more complex than when they're in series, right? And with this now, you can, if you want to calculate, let's see, I'm just saying, right? If you have a voltage here, I don't know if yes, they do have one. If you want to know the current, this I total here, they actually did it on the other page. Let me just move this aside. They did it here. Yeah. So if you want to know the current, so we added up and we got the overall resistance to be 2.86. So if you want to know the current flowing, right? I will use the convention current flowing here, I total, right? You just divide the electromotive force of the battery, which is 10. I don't know why they like 10. We're used to 12-volt batteries here. 10 divided by the 2.86 ohms, and you get 3.5 ampere, right? So it's good to know these. It's good to know these calculations. I'll tell you why it's good to know your current calculation. And the electrician guy would tell you, even if you're dealing with DC circuit, and let me tell you, right now we're going a lot with solar panels, right? And solar panels produce. Let me give you an example of what I'm talking about. Why it's good to know and understand these current calculations. Like when you just to deviate a little, right? Like if you have a solar panel 100 watt, and a solar panel doesn't produce 12 volts as some people think. You might get like, let me say 20 volts. I have 100 watt that when I check it very often, it's around 21 volts, but put it 20 volts. So in other words, this solar panel, right, is going to produce a current of, well, of course, my solar panel is not going to give me 100 watts. It's not going to give me, let's say it's going to give me 80 watts, right, on a hot day. It never gives you 100 watts. Nobody fool. So the current that it will give you is going to be 80 divided by 20, which is 4 ampere. Now, if you take, let's say you take 10 of these solar panels and hook them up in, let's say, all right, you If you put them in parallel, you're only going to get 12 volts. If you put them in series, right? Regardless of how you put them, let's say you put them in series. If you put them in series, you're going to get, well, how much watts? Let me put 100, let me say 80 by 10, 800 watts, right? If you put them in series, 800 watts. Now, this 800 watts, and it's going to actually, let me see. Let me go 20, this by 10, 200 volts. So this solar panel is going to actually have 200 volts now, right? Now, if you check this now, right? The current that is going to flow now, it's producing 800 watts divided 800 watts divided by 200 volts, and you'll get what? You'll get 4 again, right? 4 ampere, right? However, if you were to put them in parallel now, if you were to put them in parallel, something else happens now. Something else happens. If you were to put them in parallel, you get what? So this is going to produce, okay, 80 watts times 10, right? And that would be what? 800, right? 800 watts. And if you put them in parallel, it's going to produce only the 12 volt, the same 12 volt, right? It's not going to produce 200 volts like before. Now, guess what the current is going to be? I equal 800 watts over 20 volts. Look at what's going to happen here now, right? 80 divided by 2 is 40 ampere. You see what's happening there? So that's why the people who are doing these solar panel installation, they don't usually put the panels in parallel, because when you put them in parallel, the voltage remains the same 20 volts, because it's like one solar panel, right? Another solar panel, another solar panel. The voltage is going to remain at 20 volts. But remember, each is producing 80 watts. So you stick 10 of them in there, you get 800 watts. Now, 40 ampere is a large current. This could kill a man. You understand? That could cause a serious burn, fire. It could kill you, right? So you have to be careful how you wire solar panels, right? The electrician guy in the class, so what was his name? Tej Paul? Is
Yes,
he
sir.
still with us? You do that kind of work for people? Do you install panels for them?
Yes, I do industrial and commercial.
Okay, and most people would do series connections now with their panels.
Yes.
Okay, most people do that. Yes.
Yes, we do series. I do parallel.
Yes, and a lot of people go with like a 48 volt system, no? Do they?
Yeah. Yeah.
Yeah, a lot of, right now I think the Chinese bringing in,
Right,
I think
Chinese.
yeah, the Chinese, Farfan and Mendes, they're bringing in these 48 volt inverter. It's an inverter and charge controller in one. Yeah. Again, I'm deviating. You see when I get into these things. I'm not going to deal with series parallel circuits because, as I said, DC circuits, I'm saying most of you will not be working with that in your everyday life. So no need for me to get very complicated and so on. You understand the series, you understand the parallel. There are lots of series parallel circuits inside of electronics, but we're not going to deal with it, right? The last thing we'll deal with when it comes to DC circuits is power. Power in DC circuits, right? And power, there's some formulas for it, right? Power is equals to I times E. Sometimes you see P equal IV too, right? If you want to calculate the power across a particular component of a circuit, right? And alternative to that, because IE, remember E is also equal to IR, right? So E is IR. So if this I come back here, you get it's equal to I square R, right? So power is either measured by the current, by the electromotive force. If you want to know the power across, or that a particular component is going to burn, right? You multiply the current through that component by the voltage across it, right? But if you're dealing with an overall circuit, the current by the electromotive force of the entire system will say how much power is being used, right? And herein, there's another form of the equation. P is also equal to E squared over R. That's another one. But this is the one I want you to pay attention to. Because people ask why is it that we have AC current come into our house and they distribute power across the whole country, right? Using AC current and not DC current, right? And this is part of the reason. I'm going to hold back that explanation for a little later. So keep this in mind. P equal I square R. In other words, if you have a large current flowing, you're going to have a lot of power being used, right? Large current, because you notice this quantity is being squared, right? No other quantity is being squared. Watch, E isn't being squared here. Well, it's squared here too, right? But it's not, but it's divided by something. So that kind of nullifies it, right? But in this formula, you're seeing it's I square R. And the fact that this quantity is being squared, you want to make sure that when you design a circuit, I is as small as possible, right? Because that circuit is going to use more power. I mean, there are times when you have to have a large current, right? You have to have it. But generally, when you're designing circuits, you want your current to be small so that it doesn't use so much power, right? You don't want your phone to get hot, right? You don't want the only thing you want to get hot in your house is your what you call it, your iron that you iron your clothes with, right? And for that reason, the resistance of the element in your iron, your electric iron, is small enough, right, that it produces a very large current, right? But that's why when you plug in your iron, sometimes the light dim in the house, right? Yeah. But I'm going to come to why is it current is being transmitted through AC and not DC in a moment, right? So an example here, we're calculating the power in a circuit. Nope. Yeah, look here. All right, so we have a power source that is 12 volts. There's a resistance of 6 ohms. We calculate the current, right? Various ways. You can use the E square over R2 and get that, right? So they have all the ways here. 24 watts, right? So this is a low powered circuit, 24 watts. Not much, right? It's not much. Good. So what we want to do now we want to move away from DC current and start to talk about AC current. AC current, right? And in the notes, and I'm not going to get into it, because I don't want for you to get into, the physics of it and all of that, the deep physics behind it, right? But usually AC current is generated by a process called electromagnetic induction, right? Electromagnetic induction. And it is that process that what it causes electrons not to flow in one direction, but to be alternating, to be flowing in up and down, in two directions very rapidly, right? As a matter of fact, we can come to something called the frequency at which the electrons are going to oscillate in the conductor. Like in Guyana, I think they say it's 60 hertz. It means every second, those electrons are moving to and fro, to and fro, to and fro, to and fro, 60 times every second. Right? That's how it is. And how that is created, and if you go into, I want to see if, all right. They have a generator here. Let me see if I can just pull it in. They call it a 4-pole, oh my. Yeah, this is it here. It's an oversimplified one, right? So what I found out is that when a conductor, right, spins inside of a magnetic field, a current is induced in this current, this conductor here. This is like one turn of a generator, one turn. And generators would have thousands of turns, right? They wouldn't have 4 poles as you see here too. They'd have hundreds of poles. I don't know if our electrician friend worked in power generation as well, but in a real generator, they'd have, I can't say for sure how many poles they will have, right? In the magnet that they have, where this coil is spinning inside. And it will be such that it's going to produce, as we said, electricity that is 60 hertz, right? It's going to produce electricity that is 60 hertz. That's what we have in Guyana here, right? The generators we have will produce electricity that is 60 hertz. But we're not going to get into that. What this is saying basically is that the particles inside this wire here is going to oscillate. It's going to go to and fro 60 times every second, right? And if you were to plot it on a graph, right? If you were to plot it on a graph, right? If I'm going a graph here, if this is 1 second, we're going to have 60 oscillations, right? 60 oscillations in 1 second, right? And that's why for them to accomplish that, they'd have to ensure that the number of poles around here is such that it will give you this, right? But we are not into power generation. I'm just explaining to you how they came up with that 60 hertz business, right? And most equipment, most things that we buy now are fans or but what all the motors and so that we buy, right? Usually will work best with this 60 hertz. I think Guyana used to be 50 hertz at one time. And then they had to modify their whatever. I don't know what they modified. I don't think they bought new generators. They probably have other ways.
Sugar Industries right now, sir, is 50 hertz.
The what?
Sugar Industries is 50 hertz. All Sugar Industries.
Oh, because them old. Yeah, them
Because
them antiquated. Yeah, but GPL gives us 60 hertz, right? Yes, I think so. Yeah, I think so. Because I remember when there was this problem where we were buying a lot of equipment from countries that would produce equipment that works best with 60 hertz. And then they said, well, man, it's because of the difference. Those things would you'd have a fan producing a little bit of noise, the motors would not last as long, and then they eventually switched to that. But let's not get into too much of that, right? So besides the oscillation, another thing that you have to know about the AC wave is what we call the amplitude, right? And I'll bring a diagram again here. Yeah. So, so let's say this is the waveform, right? While the particles are moving, right? They're moving up and down, up and down, up and down, 60 times. The reason why this wave looks like this, it's not the particle are moving so and going down so, and it's not the particle moving here. Remember, there's a time dimension here, the time. So the particles are really moving up and down, up and down, up and down. They're not going anywhere. They're just moving up and down in the conductor, right? So you have a wire, the electrons are just moving up and down. But if you were to consider time, remember time flows forward like this, right? So you have to depict it like this, right? Now, when we hear 100 and let's say 120 volts, right? I don't know your area, what you have. If you have 110, 120, good. What that value is what I call the root mean square value. In other words, it's somewhere around here. 110 might be somewhere around here. 110 or 120 volts will be so. It's a root mean square value. It's not a peak value. The peak value sometimes is about 100 and I don't know, 170 or thereabouts, 160, 170, right? But the root mean square value is what your, like if you take a multi-tester and you test your outlet, you actually are going to get like around, yeah, I think it's around, yeah, maybe 170 thereabouts, right? But the root mean square value, let me see. Just take 120 and divide by 0.707. Can somebody do this to me? 120 divided by 0.707.
We have
169.73.
All right, good. So roughly 170 volts. Yes. So the peak voltage that you will get from your the AC power that is coming into your house is 170 volts. But if you were to take a tester, those voltmeters, and you were to test your voltage, you get 120. Why? Because the mean effect, you can see that our root mean squared is a statistical expression, right? Let's not get into it. It's going to really register 120 volts, right? So in all your calculations, really, you're going to use 120 in your calculation, right? And ask your friend there who is the electrician. You'll see that he's going to tell you that when he's doing, okay, he wants to know, well, man, what size of fuse I should use here, right? Like, let me just explain as an example. Let me see if I. One second. I'm not getting into inductors and capacitors and so, right? Because let me just give you an example of what I'm talking. In AC circuit, like, okay, the place is cold now. And a lot of people might go and buy, they have this thing, this shower attachment that they buy, right? And those things are around 3,000, they're about 3,000 watts, 3,000 watts, right? 3,000 watts. And you connect it to your shower, and guess what happens? Very often, when you put on this thing to bathe, you burn sometimes a switch. Why? Because let's say your house is 120 volts. The current that this thing is going to draw is what? 3,000 right? Remember, over 120. How much is this? 3,000 divided by 120 is how much?
25.
25 amperes this here. So sometimes some people use 20 ampere breakers. We are called oh gosh, right here, 20. The 20 ampere breaker might very well go and clicks. Your connects in your house and it cut off. At other times, if you have a bigger breaker, maybe a 30 ampere breaker, guess what? It's going to allow the current to pass, but your switch, because it can't take that. Remember, switch is wires connected in there, and that current might very well burn the switch. Right? The switches are very inferior that they have. So lots of people have this trouble because this current is too large. Notice that? But if you have a 220 system in your house, let's say you know some people got 220 as well as a 110, it might be better. It might be better to use the 220 line. So that 3,000 watts divided by 220 volts, this current is going to be half of that, around 12.5, right? And this is
13.6.
3,000 by 220, 13, okay, 13.6. 13.6 ampere, yeah. And theres sometimes the wire in your house and the switches you're using can handle it, right? So let me tell you some things like air conditioners, your microwave, your what other thing? Your water heater. You know, these things, the wiring for it, you want to ensure that the current rating of the wire is able to handle the amount of current that will flow into it, right? So you see this formula I gave you? P is equals to IV. Very, very useful formula, right? Very, very useful formula, right? And for you to, I mean, I would always defer. I'll tell you this. Don't think you can do things by yourself, right? When you're dealing with especially AC current, while you get off with DC current, right? With AC current, my advice to you, give me like Tej Paul a little work now. Call the man, right? And he's the expert and he's going to properly calculate the needs that you have, the power needs of various points, what size of wire should be used. These are very, very important things. You know, we just go like when the switch go bad, you run in and you buy that cheap what you call it, Vito switch. That thing, that thing can burn down your house. We like this duplex point, the cheap $300 one, right? It's not of the right power rating, right? And when you wire things like these shower heads that pull in about 3,000 watts, iron is about what, maybe nearly 2,000 watts, depending on. I think there's some lower powered irons coming out now. Like I think I have one that is 1,000 watts, which is very good. Right? Your microwave. Make sure you have the calculation right. Right? If need be, if you're not certain, when in doubt, make sure you call an expert. Right? Pay the man, Tej Paul a consultation fee. Right? And let him tell you what to do and so on. Possibly bring his team and do the work for you. This is one thing you don't want to make joke with. Right? AC power is serious business. Right? You know, like we in our country, we would take, they have the 220, they got a 220 outlet and they got a 110 outlet. We just buy anything and put it to anything. Right? I wouldn't lie. I have a 110 outlet, but it's really a 220. It's a one, the way they okay, let me just show you what I'm talking about. The one where you have, okay, neutral, right, live, and I think there's a whole, this is a 110, 120 volt outlet, right? The other one, there's another one where they have some, like, they have a kind of broadish, the slots for the thing to go in, right? This is a 220 or 220 volt outlet, right? right? So if you have a 110 plug, it can't fit in here, right? And if you have a 210, 220 plug, it can't fit in here. But we don't do that in Guyana. Guess what we do? We buy what we see. We buy the 110 thing and wire it into the 220 wire, right? The wire coming in there is 220. But this here is a 110 core configuration, and that's why things burning up in your house, right? So those are things, you know, you want to really pay attention to, right? And if you ever are in doubt, right? Especially dealing with, you buy a air conditioner, you buy a you know, you buy a hot water system for your house, call the experts, right? Call the experts, because THPower will tell you that for him to reach that stage where he can be a licensed electrician, you can't learn that. I can't teach you that in this 1 hour, right? No way. And that's why I'm not going to venture into it. I'm just awakening you to the dangers of AC power, right? And again, the same formula holds for AC power, right? The same formula holds, you know, P equal I square R. And that's why you want to ensure you don't want to let your currents be very large, because the power is going to be, remember, I square R, right? And that means that, okay, when I is large, the wires you got to use in the system might very well have to be fatter, right? 10 gauge. You ask, you hear about 10 gauge and 12 gauge, and so, right? And those things you have to pay attention to when it comes to safety, right? Same formula. I did say I'm going to talk about why this formula is a hint as to why we use AC to transmit power rather than DC. But before I do that, I want to talk about something called transformers, right? Transformer. Give me a second. Transform. I mean, talk about the movie here, right? Talking about, yeah. Now, transformers, because, well, transformers, what it does really, it can take a certain AC voltage and it can multiply it, right? It can multiply it. I think I think the other page, right? All right, here. A transformer can isolate your AC source from the load. That's one thing it can do, right? It can isolate it. Now, for you to do that, the number of coils over here, the number of turns in this coil, and the number of turns in this coil must be the same. Then is when you have what you call an isolation transformer. An isolation transformer. Right? And this is a very good thing. You don't see this a lot. Most people don't care about this. But this is a good thing in that it serves as a protection, right? In that it can safeguard your load, your entire house if you have. But most people can't afford, you know, an isolation transformer. We do it out. So an isolation transformer kind of separates what goes on over here with what goes on over here. The current is actually induced. As the current flows in here, it induces a current in the secondary coil, and then it goes to your house. So there's some kind of isolation, right, that goes on. And there are certain mechanisms in these transformers. You see something here, right? And they might have certain protective attachments to them that would if there is some kind of surge over here, it may not disturb what's happening over here, right? They have certain protections built in, right? Most of what we have, though, is what on the next page of our notes. The next page of our notes. talks about that. Right? As I said, this course, you have to have a whole, maybe a whole year or semester to study this kind of thing. Most of what we have in our homes is this, what we call step-up transformer and step-down transformer. So sometimes the place we're living, most of the time, like my place where I live here, I have 220 volts coming in, right? Most of my appliances in my house are 110 volts. So what I did, I bought a big, I think my transformer is it's rated for 5,000 watts, right? I have to get a bigger one because I'm buying all kinds of things in this house, and I noticed the other day it was getting pretty warm, right? And a lot of people go at 10,000 watts. And what they'll do is they'll have what you call a step-down transformer, right? They'll have a step-down transformer. The transformer step down 220 to 110, right? It will step down from 220 to 110, right? And I'll tell you
Right?
something. Yes, sir. Yes.
Instead
Tell
of
me.
buying a transformer, you could buy AVR.
Okay. Tell me about that.
Yeah. It's an automatic voltage regulator. It's better than the transformer.
Oh, well, to be honest, boy, yes, I do see them around. And they're rated this high, 10,000 watts.
Yes, you got them in 10,000, yeah.
But I wonder what their price is because
About 80,000 as one.
oh gosh, nice. Like he's selling this thing or what? You're
No,
right,
man.
right? And I think the reason why you're recommending it, besides the isolation aspect, right? It has certain built-in controls that deals with surges and so, right? Is that why you're
Yes,
recommending
the
it?
AVR is better because you get a contact and thing inside contacts and stuff.
Yes, I think I know that's where you're coming from. Yeah.
So,
So
sir,
yes.
but I think the regulator is just to regulate the 110 or the 220. The transformer now is will break it down from 220 to 110 or build it up from 110 to 220.
Oh no, they have those that also do 220 to 110 and 110 to 220. They have all kinds, Yeah. It will do both the step up, step down, and the regulation. They have that too.
The AVR does both.
Yes. But you hear the price, right? But again, I'll tell you, if you have the money to invest in these things, right? For safety's sake, right? And sometimes in the long run, you save your equipment in the house, right? When a fridge burns, you know how much for a fridge? $200,000-$300,000 for a fridge, You understand? When something goes wrong in there. But if you have these things in your house, they can help. Yeah, so what I did, I converted the 210 to 110 in my house, 220 to 110. And most of my my fridge, I think my fridge, my microwave, the iron is 110. I don't have much though, right? I think I have a freezer here, it's 110. Yeah. Oh, and by the way, there's a I'm not gonna get into this. There is a relationship that shows you when they're designing the transformers, right? The relationship between the number of turns. But I wouldn't get into it, right? I wouldn't get into it. I'll tell you though, the Chinese are very smart, right? And am I calling the boy your right name? Tejpal? I'll tell you what the Chinese are doing. The Chinese are not having what you call primary coil and secondary coil. The transformer I have is not no primary and secondary. It's one long coil. So this is this is 220 here, right? 220 volts. And they put a center tap like this. And they take off 110 volts. Right? 110 or 120 or whatever it is. So they don't use two coils. They use one big coil and take a center tap. That's what the Chinese did. And I didn't know it. My friend was warning me. And when I actually wired it up, I'll tell you what happened. I bought my fridge, and when the guy plugged in the thing, right? When the guy plugged in the thing, no, before he plugged in, he tested my point, and he said that your neutral is live. I said, what? And he said, yes. And he said, you know why? You think that you have an isolation transformer, but no. The Chinese transformer is one big coil, and they just put a center tap. So you're having a lot of losses here. Because this thing is, all this thing is doing is heating up. And that's why my transformer gets very hot. And I have a few friends who buy the same Chinese transformer, and it gets very hot during the day. But not during the day, all the time. Right? But I'm not going to get into that. But let's talk about transformers. Right? And transformers work with AC. Transformers convert AC. In other words, you can take 220 volts and step it up to 22,000 volts and all. You could do that because of the power of transformers, right? So transformers can take a small voltage, right? I don't know how much the generator at GPL, what they produce. I think they do three-phase power. I don't want to get into all of that. And they step it up to, is it 60,000 volts, friend? 60,000 volts?
Yeah.
Somewhere here, either 60 or 66,000 or something like that volts. The transformers do that, right? It takes the small voltage, if it's 220 or 480 or what they produce, and step it up to 60,000. Now, why? Why? Remember this formula? All right. V equal IR and P equal I square R. So, watch this. If you have a transmission wire that has a certain resistance, if the voltage, right, is very, very high, right? If the voltage is very high, V is equals to I, yes. What that allows you to do is to limit the current, right? Okay, let's take this, right? I want to go to, I think I used the wrong formula. P equal IV. This is the one I want. P equal IV. So if you were to take this now, right? V is equals to, what am I saying? P over, no, I'm wrong. I is equals to P over V, yes. So let's say you're transmitting 1 megawatt, right? 1 megawatt, which is 1 million watts, right? And the voltage is 66,000. What will the current be? You're transmitting 1 megawatt at 66,000 volts. What will the current be in the wire that is transmitting 1 megawatt? So we can strike off these zeros. We can strike off these zeros. What do you get here? 1,000
So
divided by
15.15.
All right. Let me go with 15 amperes. Just imagine we are transmitting 1 megawatt over a piece of wire at this voltage. Look how small the current is. Right? On the other hand, right? And that's the current. So the power loss in the wire is going to be this, right? It's going to be I squared by R. It's not going to be so much, right? The current is very, very small, right? And the reason why is that you were able to step it up to 66,000 using a transformer. With DC current, you can't do that. right? We don't have transformers that will step up. Oh, by the way, I am speaking a little, I want to tell you there are research, right, that actually is in progress now that is making transmission by DC power possible, right? So the current research is actually able to step up DC to a very high current, sorry, a high voltage. But as of now, in every day in our country here, if you were to use DC power, and let's say the DC power is even 48 volts, look at this voltage. If you want to, watch this, if you want to transmit, what? Even if you were to, let's say those solar panels that they have, and the, let's say you go up to 200 volts, I'm just saying, right? 200 volts. And you want to transmit 1 megawatt of power. 1 megawatt. Let's say you have a 1 megawatt of DC power, and it's at 200 volts, right? Watch what would happen. So I will be equal to that. 2 gone there. So you have 10,000. This is what, this is
5,000.
5,000 ampere. This, you know, there's no wire in the world that could carry 5,000 ampere. It's gonna burn up, and they're gonna kill everybody that's working with it. You see? So DC current, because we have no way of stepping it up and stepping it down at will, it's unsuitable for large power transmission, right? It's unsuitable. But as I'm saying, there is research now, right? There is research that is going on to step
Sir,
up and
but
step down.
sir, but if it's not possible, how the solar grids does work really?
Well, what they do, the solar grids, right? They have, okay. Remember I was telling you of these inverters that they're making? These like 48 volt inverters.
Yes, sir, I
They have
know
some
about
of them.
the small inverters that does use the 12 volt and the 24 and the 48.
No, not
But
those, not those. They got some that would work with 40. You got some that would work with as much as like 200 volts and so. Some of them go higher than this. What they will do is connect these, they'll connect these in series, like, right? So they'll wire so many panels to one of these inverters. Then they'll take the next set. If you were to go my place, University of Guyana, there, they have solar panel on the entire roof. But in the control room, they have about, I have about 6 of these inverters, and they're all wired in parallel. So each one of them will take off like about 200 volts, right? And it will convert it to what we want, the 110 or 220, you know? So yes, but as I said, right, these large installations, they have the electronics to deal with it, to convert it to AC, right? They convert the DC current from the solar panels to AC. And then they step it up to 66,000 and whatever else, transmit it, then step it down back to 220 or 110, and then use it. Right? So that is why we're using AC current to transmit power to your homes and so on. As a matter of fact, my good friend the electrician would tell you that from certain calculation, DC power transmission, actually, we have less loss than AC power transmission. But the trouble with DC is the stepping up and stepping down that is troublesome. But AC, even though we're having a lot of loss in the wires, right? You can easily step up and step it down using powerful transformers, right? So keep the relationships we had in we talked about, right? The P equal, what is it? P equal what were they? IV, P equal I square R, right? This kind of thing, right? P equal, what was it? E square over R, was that one of them? Yeah. Know how to use these formulas, and also that you can do basic calculation with electrical systems, right, and circuits. Right, and lastly, we want to talk about is how we measure electrical energy, right? Electrical energy, right? And all of you know, like when you buy current or you buy electricity to run your house, it's normally measured in what? Kilowatt hour, right? Kilowatt hour. And what this is basically telling you, right? Remember that? Watch. Energy, remember he said P is equals to IV, right? IV. But energy is equals to power by time. Power by time, right? Power by time. So remember, kilowatt, that's power. And the time is in hours, right? So they don't use seconds. They use power in terms of kilowatts, and the time is measured in hours, right? And I think 1 kilowatt hour is roughly what now? It's about what? About $55 or something like that. And if you use too much, they kind of raise the price to $75 or something like that, depending on how much you use. So if you have like, all right, let's say you have an air conditioner. I'll show you how those things drink power. And the air conditioner is 2,000 watts, right? In other words, it's 2 kilowatt. And you are running this air conditioner from the time you land home in the evening, you land home 5 o'clock. And some people run it whole night, some people by half night, let's say to midnight, no? To 12. Let's say you run it until then. That's how much? 7 hours? So 2 kilowatt by 7 hours. 7 hours would be what? 14 kilowatt hour, right? Multiply that by, I'm going to charge you this higher rate because over the month you're going to be burning a lot. So around $75 per. So one night you're using about 14 by 75 is how much? How much is that?
1050.
14. How much?
1050.
1050.
1,000. All right, let me go with 1050. All right, $1,000 a night to run your air conditioner. Right? And remember, you have all appliances in the house. You got your fridge running 24 hours. You got your freezer running 24 hours. Some people run the air conditioner 24 hours too. And there's a small air conditioner, you know. There's 2,000 watts. Right? The small one. And I think I just want to mention this, right? This is not part of our course. I want to tell you this. This country is setting themselves up for terrible problems. Right? Everybody building with concrete. And what we're doing is basically making a set of ovens. Our houses are ovens, giant ovens. It absorbs all the heat during the day. And you have to now run air conditioners to cool it down, you know, to feel comfortable inside. And we're going to run up some terrible power bills, right? So while concrete houses might, yeah, in the long run, in terms of maintenance, might be less than a wooden house, to air condition and is very costly. And secondly, the designs of our houses. Oh God.
Yes, the energy, sir. Cheaper rate.
You sure? You sure we got all right? Here what? Right now, $5,000, right? For a bottle of gas. When the gas energy project come on board, y'all must find me wherever I am in Guyana. And let us see if it will be less than $5,000. You make me remember when they build the bridge, right? A friend of mine said, "Bye, when we build the bridge, we go drive over, we go pay $100." And so when the people slap them $2,000, by look, I don't know where some people nearly faint away. The reason why is that The people borrowed people money, people invested billions of dollars, and the people want it back. There's something named profit, like people don't understand this. That gas to energy project they're doing there is costing billions. As a matter of fact, they're ending up in some very complicated situations, right? That making the project run up in cost far more than they anticipated because of the place they use. So when they finish, you think they're gonna sell gas for $100 to you, buy, or $1,000 to you? They have to recoup those billions of dollars, and they have to make something in profit. Like you, I don't understand that. And then there's something in inflation. So when, all right, I'll bet any one of you, gas is now 5,000. When the gas to energy project finish, y'all find me, right? Find me and tell me if it's less than 5,000 for a bottle of gas. Right, friend? Right, friend?
Yes, sir. Yes, sir.
Must find me and tell me and watch, must tell me if electricity drop below the $53 per kilowatt hour. Right? Must find me and tell me if this go down from this. Right? I never, let me tell you something. If you know economics, nothing goes down in price. Right? Nothing goes down in price. If gas is $5,000, no, there's no way when they finish that project around 2030, it's going to be less than 5,000. Whoever tell you that, they're fooling you. All right, good. Hey, I shouldn't say all of this on this recording.
Sir, so basically, they're selling me dreams.